Alright, we're going to look at some graphs of more inverse functions. I said in the last video that inverse functions, the graphs are reflections across the line y equals x, the diagonal line. And so some kind of more obvious inverses are some things we saw in the library of functions, like if you had x cubed, for instance, a cubing function, we know that that function looks like this. It's kind of a half parabola going up and half parabola going down. They're not exactly parabolas, but it kind of looks that way. And then its inverse is the cube root function, and of course that one we've seen is the same similar shape, just laying on its side. And so those two functions definitely have the same reflection property, right? If you drew a diagonal line from the origin, and maybe this is going to turn out poorly, kind of going through the intersection point there, I'm going to jump in that small section there. I'm not going to fill it in, but you can kind of see the reflection across that line y equals x, right? Y equals x, of course, is a line with a slope of 1 and a y-intercept of 0. So it goes through the origin, goes up 1 over 1, all the way down. And what's interesting about that line is every point on that line has the same x and y coordinate, like 1, 1, 2, 2, 3, 3, and so forth. Okay. So those two functions, have that same reflecting property. If I move over to another set, I could just make up a set, really. Let's take a function. I'll call. Let's go like the point 1, 4, and let's connect it to the point maybe at -3, 0, and maybe I'll just draw some sort of weird curve going down. Well, as soon as I know a couple points in the general shape, then I can find the inverse of this. Let's call this one f of x. Well, I can find its inverse by just interchanging the 2 points. So if 1, 4 is on the graph of f, then 4, 1, I'll go right over here somewhere, 4, 1 is on the graph of the inverse. And if -3, 0 is on the graph of f, then 0, -3 must be on the graph of the inverse. And so if I connect those, you probably already see where this is going. I can connect these 2 points, and you'll see that same sort of symmetry show up. Now, of course, this is a rough sketch. It's not going to be perfect. But if you were to sketch the line going through on a 45-degree angle through the origin, it will hit the point of intersection. And in theory, these points are a reflection across that line. What I mean by reflection, and of course it's not drawn perfectly, but what I mean by reflection is that these, if you draw a segment between the two between the 2 points, you'll get a 90-degree angle, and you'll also get the distances on either side being the same. Okay, again, that's not perfectly drawn, but this should be a 90-degree angle here, and the 2 distances should be the same. Okay. Alright, so now there's another one. If x cubed and the cube root are inverses, then it would make sense, at least at first glance, to say that the x squared and the square root functions are inverses. But just for a moment here, I'm gonna assume that's not the case. I'm gonna call them f and g. And we'll see some interesting things that happen here. With the x squared function, we know that that's a parabola. Starts at the origin, opens up. Okay. So that's our x squared function. Now the square root function is interesting because if I were to try and reflect the x squared function across the line y equals x, you're going to get part of that function going up and to the right. Okay, that's the reflection of this right half. But the reflection from the left half is going to go down and to the right. Now that's a problem. Why is that a problem? Well, the square root function doesn't have a lower half. That doesn't exist on the actual square root function. The reason for that is you can't get negative values out of a square root. Right? No matter what I plug in for x, there's only positive outputs. Furthermore, this would violate the vertical line test. Right? The function on the right is not actually a function at all. So square root, well, I shouldn't write it that way. I should just say that the blue graph fails the vertical line test. You guys all know VLT is my abbreviation for vertical line test. So the blue graph fails the vertical line test. So it's not actually a function at all. So that means that the square root of x and x squared are not inverse functions. They're actually not inverse functions. So how do I know? I mean, those seem like they would work if x cubed and cube root work. And the problem is that this x squared function does not pass something called the horizontal line test. If this other one fails the vertical line test, these 2 points must reflect from points that line up horizontally. Okay, and so they fail what's called the horizontal line test. Okay, so x squared fails the horizontal line test. It's similar to the vertical line test we learned before, just with horizontal lines. And what you'll find is that if a function fails the horizontal line test, it will not have an inverse. So as a general rule, if a function fails the horizontal line test, then it cannot have an inverse function. Okay, the resulting inverse would not pass the vertical line test. Okay, so the functions that do pass the horizontal line test are called one-to-one functions. They have a special name. So functions that pass the horizontal line test are called 1-to-1 functions. Okay. Now, for short, I usually abbreviate that 1-1, right? 1-to-1. Okay, so a 1-to-1 function will have an inverse, and they will also pass the horizontal line test. So 1-to-1 functions pass the horizontal line test and have inverse functions. Okay. Cool. The last thing then is that you can have an inverse related to the x squared and the square root. You just have to be careful how you define things so that the x squared and the square root are only inverses on a certain part of the domain. So if you look at f of x being the x squared function for x greater than or equal to 0, just the positive side with 0, then you actually do have an inverse with the square root of x. Okay, so you just have to restrict the domain, limit the graph to part of the graph that passes a horizontal line test.